variables are not always constant, and so the use of integration will help us see the definite values of these two variables. Later on, I'll be giving an example of how integration is being used in finding the variables of work.
Problem is, a cable that weighs 2 pounds per feet is attached to a bucket filled with coal that weighs 800 pounds. The bucket is initially at the bottom of 500 feet mine shaft. The first question now is, determine the amount of work required to lift the bucket to the midpoint of the shaft. The second one is to determine the amount of work required to lift the bucket from the midpoint of the shaft to the top of the shaft. The third question is to determine the amount of work required to lift the bucket all the way up to the shaft. Before solving the problem, the first thing that we need to know is that at any point of the shaft, the expression will always be 500 minus x. And with the given weight of the cable, which is 2 pounds, we can now make an expression of 2 times the quantity of 500 minus x. After getting the expression of the weight of the cable, we can now proceed to making the equation of the force. As we all know, force is equals to the weight of the cable plus the weight of the bucket. And with the expression of the weight of the cable, which is 2 times the quantity of 500 minus x, and with the weight of the bucket, we can now have the final equation of force, which will become 1,800 minus 2x. After getting the equation of the force, we can now then proceed to the first question, which is determining the amount of work required to lift the bucket to the midpoint of the shaft. So it will now begin from the very bottom up to the midpoint of the height of the shaft. So the equation will look like work is equals to function of x dx from 0 to 250 feet. You will just substitute the value of function of x and will now become 1,800 minus 2x dx from 0 to 250 feet. You'll just integrate it and it will have an answer of 1,800x minus x squared from 0 to 250 feet. After that, you'll just substitute the values of x, which are 0 and 250 feet. And finally, you will have an answer of 387,500 pounds per feet. Moving on to our second question, which is determining the amount of work required to lift the bucket from the midpoint of the shaft to the top of the shaft. So it will now begin from the midpoint all the way up to the top of the shaft. The process is still the same. You will still use the equation of the work, which is the function of x dx from A to B, or from 250 to 500 feet. After that, you will just again substitute the equation or the function of x, which is 1,800 minus 2x dx from 250 to 500 feet. After that, you will just integrate it and you'll come up with an answer of 1,800x minus x squared from 250 feet to 500 feet. After that, you will just substitute the values of x, which are 250 feet and 500 feet. And finally, you will be able to come up with an answer of 262,500 feet or 500 pounds per feet. After answering the second question, you now then proceed to the third and last question, which is to determine the amount of work required to lift the bucket all the way up the shaft. The process is still the same, that the variables are now different. All the way up the shaft, so we'll begin from 0 all the way up to 500 feet. So the formula will be W is equals to function of x dx from 0 to 500 feet. Now you'll just substitute the value of function of x. It will become 1,800 minus 2x dx from 0 to 500 feet. After that, you'll just do the integration. So it will become 1,800x minus x squared from 0 to 500 feet. After that, you'll just substitute the variables. And now the final answer will become 650,000 pounds per feet.
That's it, guys. I hope you learned something and see you again next time. This is Samantha Jumamil signing off.